This security pitfall is related to transaction order dependence, or TOD for short. Recall that in Ethereum, transactions submitted by users sit in a data structure known as the mempool and get picked by the different miners for inclusion within blocks. The specific transactions that are picked and the specific order of those transactions included within the blocks depends on multiple factors, and specifically the gas price of those transactions itself. So from an attacker's perspective, one can monitor the mempool for interesting transactions that may be exploited by submitting transactions with gas price appropriately chosen, so that the attacker's transaction either executes right before or right after the interesting transaction. This is typically known as front running and back running, and may lead to what are known as sandwich attacks. And all these aspects are related to assumptions being made on the transaction being included in a specific order by the miner within a block. So from a security perspective, logic within smart contracts should be evaluated to check if transactions triggering that logic can be front run or back run to exploit any aspect of it. A classic example of transaction order dependence is the proof functionality in the popular ERC20 token standard, which we shall take a look in the next slide. Recall that the ERC20 token standard has the notion of an owner of certain balance of those tokens, and there's also the notion of a spender, which is a different address that the owner of tokens can approve for a certain allowance amount, which the spender is then allowed to transfer. And this approval mechanism is susceptible to a race condition. So let's take an example to see how that works. Let's say that I am the owner of a certain number of tokens of an ERC20 contract, and I want to approve a particular spender with 100 tokens of allowance. So I go ahead and do that with an approve 100 transaction, and later I change my mind and I want to reduce the allowance of the spender from 100 to 50. So I submit a second approve 50 transaction, and if that spender happens to be malicious or untrustworthy and monitors the mempool for this approval transactions, they would see that I'm reducing their approval to 50 by noticing the approve 50 transaction. In that case, they can front run the reduction of approval transaction with a transaction that they send that spends the earlier approved 100 tokens. So that goes through first because of front running, and when my approve 50 transaction goes through, that would give the spender an allowance of 50. Now the spender would further go ahead and spend those 50 tokens as well. So effectively, instead of allowing the spender to spend only 50 tokens, I have let them spend 150 tokens of mine. And this is made possible because of transaction order dependence or front running. The mitigation to this, the best practice recommended is to not use the ERC20 approve that is susceptible to this race condition, but to instead use the increase allowance and the decrease allowance functions that are supported by such contracts. This security pitfall is related to the use of the ecrecover primitive in EVM and supported by Solidity. And the specific pitfall is that it is susceptible to what is known as signature malleability or non-unique signatures. Recall that elliptic curve signatures in Ethereum have three components, V, R, and S, as shown here. And the ecrecover function takes in a message hash and the signature associated with that message hash and returns the Ethereum address that corresponds to the private key that was used to create that signature. In the context of this pitfall, if an attacker has access to one of these signatures, then they can create a second valid signature without having access to the private key to generate that signature. And this is because of the specific range that the S value or the S component of that signature can be in. It can be in an upper range or a lower range, and both ranges are allowed by this primitive, which results in the malleability. And this, depending on the logic of the smart contract and the context in which it is using these signatures, can result in replay attacks. So the mitigation is to check that the S component is only in the lower range and not in the higher range. And this mitigation is enforced in OpenZeppelin's EC-DSA library, which is the recommended best practice. This security pitfall is related to the transfer function of ERC20 tokens. The ERC20 specification says that a transfer function should return a Boolean value. However, a token contract might not adhere to the specification completely and may not return a Boolean value, may not return any value. And this was okay until the Solidity compiler version 0.4.22, but any contract compiled with a more recent Solidity compiler version will revert in such scenarios. So the recommended best practice for dealing with this scenario is to use the safe ERC20 wrappers from OpenZeppelin for such interactions. This pitfall is similar to the previous one and applies to the owner of function of the ERC 721 token standard. The specification says that this function should return an address value. However, contracts that do not adhere to this specific aspect would return a Boolean value, which used to be okay until the Solidity version 0.4.22, but with any newer compiler version, returning a Boolean value would cause a revert. So the best practice again is to use the ERC 721 contract from OpenZeppelin. This security pitfall is related to the ether balance of a smart contract and how that can change unexpectedly outside the assumptions made by the developer. Recall that smart contracts can be created to begin with a specific ether balance. And there are also functions within the smart contract that can be specified as being payable, which means that they can receive ether via message value. These two ways can be anticipated by the developer to change the ether balance of the contract, but there are also other ways in which the ether balance of the contract can change. One such way is the use of coin-based transactions. These are the beneficiary addresses used in the block headers, where the miner typically specifies the address to which the block rewards and all the transaction gas fees should go to. And that Coinbase address could point to a specific smart contract where all the rewards and the gas fees go to if that block is successfully included in the blockchain. The other unexpected way could be via the self-destruct primitive, where if a particular smart contract is specified as the recipient address of self-destruct, then upon that executing, the balance of the contract being destructed would be transferred to the specified recipient contract. So these two ways, the Coinbase and self-destruct, although very unusual and unexpected, could in theory change the ether balance of any smart contract. And this could be well outside the assumptions made by the developer or the team behind the smart contract. So what this means is that if the application logic implemented by a smart contract makes assumptions on the balance of ether in this contract and how that can change, then those assumptions could become invalid because of these extreme situations in which it can be changed. So this is something to be paid attention to while analyzing the security of a contract from the perspective of the ether balance that it holds. This security consideration is related to the use of fallback and receive functions within a smart contract. Recall from our discussion in the solidity modules that there are differences between these two functions. There are some similarities, and these are related to the visibility, the mutability, and the way that ether transfers are handled by these two different functions. So from a security perspective, if these functions are used in a contract, then one should check that the assumptions are valid, and if not, what are the implications thereof. From a security perspective, strict equalities are considered as dangerous in specific contexts of the smart contract applications. Strict equalities refer to the equal to operator or the not equal to operator as compared to the less stricter, less than or greater than or equal to operators. When these strict equalities are applied to ether or token values, then such checks could fail because the transferred ether or tokens could be slightly less or greater than what the strict equalities expect, or the balances computed could be different because of the different number of decimals expected, or the precision of the operations being slightly different from the assumptions being made. Hence, the use of strict equalities with such operands and operations is considered dangerous because they could lead to failed checks. So the security best practice is to default to less stricter equalities and make sure that those constraints are satisfied as per the assumptions. Locked ether refers to the situation where the contract has an ether balance that gets locked because ether can be sent to that contract via payable functions, but there's no way for users to withdraw that ether from that contract. And this is, in a very simple scenario, possible when smart contract has functionality to allow users to deposit ether, but there is no functionality to withdraw the ether from that smart contract. The obvious solutions are to remove the payable attributes for functions to prevent ether from being deposited via those functions, or to add withdraw capabilities to the smart contract. The simple situations for this particular pitfall can be easily recognized and fixed, but there could be complex scenarios where the contract can be taken to a particular state, either accidentally or maliciously, where the ether or the token balance of that contract gets locked and cannot be withdrawn. The use of transaction origin is considered dangerous in certain situations within smart contracts. Recall that in the context of Ethereum, transaction origin gives the address of the externally owned account that originated the transaction. And if this address, the transaction.origin, is used for authorization, then it can be abused by attackers for launching replay attacks by coming in between the user and the smart contract of concern. This is sometimes known as man-in-the-middle replay attack, or MITM as an abbreviation, because the attacker comes in between the user and the contract, captures the transaction, and later replays it. And because the smart contract uses transaction.origin, it fails to recognize that this transaction actually originated from the attacker in the middle. So in this case, the recommended best practice for smart contracts using authorization is to use message sender instead of transaction.origin, because message sender would give the address of the most recent or the closest entity. So in this case, if there is a man-in-the-middle attacker, then message sender would give the address of the attacker and not that of the authorized user pointed to by transaction.origin. There may be situations where a particular smart contract may want to know if the transaction or the call made to it is coming from a contract account or an externally owned account. There are two popular ways for determining that. The first one is to check if the code size of the account of the originating transaction is greater than 0. And if this is not 0, it means that that account has code and therefore is a contract account. And the second technique is to check if the message sender is the same as the transaction origin. And if it is so, then it means that the message sender is an externally owned account, because recall that transaction origin can only be an externally owned account in Ethereum as of now. So these two techniques have pros and cons, and depending on the specific application, it may make more sense to use one over the other. There are risks associated and implications thereof of either of these two approaches. Particularly with the code size approach, the risk is that if this check is made while a contract is still being constructed within the constructor, the code size will still be 0 for that account. So if we determine based on that aspect that this is an externally owned account, then it would be a wrong assumption. The next security pitfall is related to the concept of the delete primitive in Solidity and how it applies to mappings. If there is a struct data structure in a smart contract that contains a mapping as one of its fields, then deleting that structure would delete all the fields of the struct, but the mapping field itself would remain intact. So this is one of the Solidity's behaviors that needs to be kept in mind, and that can have unintended consequences if the developer assumes that the mapping field within the struct also got deleted and reinitialized to its default values. The best practice is to use an alternative approach, such as considering the data structure that is meant to be deleted as being locked to prevent future logic from using the data structure or the mapping fields within that data structure. An interesting security consideration is that of tautologies and contradictions. A tautology is something that is always true, whereas a contradiction is something that is always false. And within smart contracts, if there are certain primitives used, such as the example shown here, where there is an unsigned integer variable x, and then there is a predicate that checks if x is greater than or equal to 0. Now this predicate, because of the type of x being an unsigned int, is a tautology. It's always going to be true because x cannot take a negative value. The presence of such tautologies or contradictions in smart contracts indicates either flawed logic or mistaken assumptions made by the developer, or these may just be redundant checks. In either scenario, these may be interesting from a security perspective, so it is something to be paid attention to and flagged as potential concerns. The use of Boolean constants, true or false, directly in conditionals is unnecessary. And the reason for that is if there's a conditional whose predicate is true, then that can be removed because that code block would get executed nevertheless. And similarly, if the predicate is the Boolean constant false, then that could be removed as well, and along with the code in that associated block, because that code would never execute because the conditional is always going to be false. So these usages of Boolean constants, specifically within conditionals, is indicative of flawed logic or assumptions, or they could just be used in a redundant manner where upon identifying such usage, one can recommend removing those constants and any code blocks associated with them so that it becomes simpler to read and to maintain. An aspect related to Boolean constants is that of Boolean equality. This is where the Boolean constants true or false are used within conditionals for an equality check. So as shown here, the x variable is checked against the true constant. Now this usage is redundant because the variable x can be used directly within the conditional's predicate without actually comparing it to true. And both of them are equivalent, so the use of the Boolean constant true within the predicate is actually unnecessary. So while this may not be a big security consideration and perhaps indicative of the developer not fully understanding how Solidity's Booleans work, it is interesting from an optimization perspective and certainly improves the readability aspect of the code. Contract state modifications made in functions whose mutability is declared as view or pure will revert in contracts compiled with SolC version greater than or equal to 0.5.0. This is because this compiler version started using the static call opcode for such functions, and this instruction leads to a revert if that particular function modifies the contract state. So when analyzing the security aspects of contracts, it's good to pay attention to the mutability of the functions to see if they are view or pure, but they actually modified the contract state, in which case they would lead to reverts at runtime. Checking the return values of functions at call sites is a classic software engineering best practice that's been recommended over several decades. And in the case of Solidity, this specifically applies to return values of function calls made using the low-level call primitives. These are the call, delegate call, and send primitives that do not revert under exceptional behavior, but instead return success or failure as a return value. So because of this particular characteristic, it becomes critical for the call sites in contracts that use these primitives to check the return values and act accordingly. If not, it could lead to unexpected failure. Checking for the existence of a smart contract account at a particular address before making a call is a security concern. And the reason for that is because when such calls are made using low-level call primitives, call, delegate call, or static call, these functions return true even if the account does not exist at that address. So if the contract making such a call looked at the return value, saw it was true, and assumed that the target contract existed at the address that it called, and also assumed that the contract executed successfully, then that would be a faulty assumption. And this, as you can imagine, could have some serious implications to security. So the best practice here is before making low-level calls to external contract addresses, one should check that those accounts do indeed exist at those addresses. Shadowing of built-in Solidity variables was a concern in some of the older Solidity versions. Built-in variables such as now, assert, and some others could be shadowed by other variables, functions, or modifiers in the contract to override their behavior. This, as you can imagine, is dangerous and could lead to many unexpected behavior, and therefore this shadowing was disallowed in the later Solidity version. Similar to the shadowing of built-in variables, the older versions of Solidity also allowed state variable shadowing. This meant that derived contracts could have state variables that had the same name as some of their base contracts. So you can imagine that the base variables and shadowed variables with the same names could be confusing even for the developer, and they could end up using or modifying the wrong variable from the base contracts. This dangerous and unexpected consequences was recognized. So Solidity compiler 0.6.0 disallowed shadowing of state variables.